Okay, Assalamualaikum and very good day to all of you. So today we're going to continue with our next lesson. We're still in chapter 1. Okay. Okay, so in this part, which is part 6, we will learn about surface tension. Okay. The easiest way to see the phenomena which is caused by surface tension is by looking at the water drop here in this diagram, in which that you can see that the water molecules hold tightly to each other. Okay, it seems like there's a force which is try to squeeze them and hold the molecule tightly together. Okay, so why it happened basically. In order to understand about the surface tension which is exists in the liquid, okay, so we can use this diagram, okay. So for example, here is the liquid in which that there is a molecule, the liquid has a molecule on the surface, and in fact this is the molecule of the liquid. There's a force which is involved here, okay, which is it has the tension force, okay. And actually the liquid drops is behave like a small balloon which is filled up with liquid and leave it on the solid surface, okay. So if we close look this image, it will exactly look like this, okay. Why? So if you look at the area here, okay, it seems like it is in under tension force, okay. So the area here, so the surface of the liquid is acts like a stretched elastic membrane under tension. Of course, when you try to push it, okay, there's a force. Try to rebound back, okay. So why this thing happen? So this thing happen because of the pulling force which is exists in the liquid, and it is due to the attractive force between the molecules in the liquid, okay. And in fact this attraction force is actually act in parallel to the surface, okay. So I hope that you can understand the concept of surface tension which is exists in the liquid. And in this slide we can see the examples of the existence of the surface tension. For example, like a drops of water beading up on a leaf in the morning and the water strider sitting on the top of the water, okay. So look at this water drop, okay, or dew that you see in the morning, okay. So it will form like this because of the surface tension exists on the surface of the molecule here, water molecule, okay. And the second one, which is the kind of like insect, usually we see it in a river, okay. So how can this insect can walk on the surface of the fluid, okay. Can a human walk on the surface of the water like this? You won't be able to walk on the water because there's a certain limitation, because the surface tension here maybe is not enough to support your weight of the body. So as I mentioned just now, the surface tension which is exists on the film surface of the liquid, okay, is actually caused by the attraction force of the particles. So basically what happened is the particle which tend to minimize its surface area, okay, by using the attraction force between the particles and make the existence of the surface tension. And usually this thing is measured per unit area, okay, and the unit for surface tension is Newton per meter. Okay, so in this part, we will cover about the viscosity, in which that in viscosity we have two types of viscosity, which is dynamic viscosity and the other one called as the kinematic viscosity. So what's the difference between dynamic and kinematic viscosity? Okay, let's check it out. So let's understand first what is viscosity. Okay, so viscosity is actually can be simplified as a resistance which is exists in a fluid during motion. Okay, so the simplest way to explain about viscosity, okay, imagine that you are pouring two types of liquid. For example, the first one is honey. Okay, so you pour it on the slanting surface. Okay, and the other second liquid is which is maybe like water. Okay, so you set time. Okay, so which liquid will reach this point faster? Of course, the water will reach faster because the water has less viscosity. Okay, compared to honey. Okay, so why? It is because of the internal resistance which is inside the liquid here, inside the water, the molecule of the liquid, which is give an effect towards the motion of the liquid. And the second term is drag force. The drag force is actually the force of a flowing fluid exert on the body in a flow direction. Okay, so for examples, the water, look at this example, the first example. Okay, the air flowing in this direction, and the eagle, okay, is flow in opposite direction. Okay, so there will be a friction, okay, between the air and the eagle body. Okay, so the friction force here is actually, we call it as a drag force. Okay, so the magnitude of the friction force here is actually strongly depends on the viscosity of the solution. Okay, so try to imagine, will it be easier for the eagle to fly in the air, or if the eagle want to fly in the water? Which one is more easier? Of course, in the air is more easier because the air has low drag force towards the eagle body compared to water. Okay? Okay, let's understand about the dynamic viscosity. Okay? So before we learn about dynamic viscosity, we have to know first the existence of the shear stress, in which that shear stress is actually defined as a force required to slide one unit area layer of a substance over one another. Okay, so this shear stress is actually developed when the fluid moves, and the magnitude of this force is actually depends on the viscosity of the fluid, and is quite similar to the concept of the drag force that I explained in the previous slide. Okay, and the unit for the shear stress is actually Newton per meter square. So how can we determine the dynamic viscosity? Okay, so again it relates back with the velocity gradient, in which that it refers to the change of velocity with the change of location or point of the location. Okay, so velocity gradient in this case is actually the difference in velocity divided by the difference in the point of location, and this velocity gradient is also called as a shear stress. Okay, so if we look at this diagram, the velocity change here is refer to this one, so the range here, okay, in which that there might be a velocity change, okay, happen at this region, okay, and it is divided by the delta y here, which is a refer to the distance, okay, the change in distance when the liquid moves, okay, in this direction, right? And the shear stress here is actually can be derived through this equation. So this is the shear stress, which is we reflect that as a velocity gradient, okay, and here it is actually where we can get the dynamic viscosity. So from the formula of shear stress, we will be able to determine the dynamic viscosity. Okay? And usually the dynamic viscosity is always referred in the unit of poise or centipoise. Okay? And in the SI unit for the dynamic viscosity is actually, so what is the dynamic viscosity? Okay, so before we can determine the dynamic viscosity, we have to understand first the concept of shear rate, in which that the shear rate, which is the force, okay, on the surface of the liquid, which is can be determined by using the relation of velocity gradient. Okay, so imagine that there is a liquid flowing inside between these two plates, in which that this surface is stationary and this surface is moving in this direction. Okay, so of course there will be a drag force occur here, in which that we can determine the shear rate happen in this liquid. Okay, so if you look at this diagram, okay, there will be a change in velocity gradient. Okay, there will be a change in velocity as the distance change. Okay, in fact, sometimes when you see in the water, in a pipeline, okay, so the gradient will be look like this. Yeah. Okay, so the change in velocity gradient is directly can be used to determine the value of shear rate, okay, happen in this liquid, okay, in which the shear rate is proportional to the velocity gradient. And here we can determine the value of dynamic viscosity. Okay, so therefore, the behavior of a fluid in laminar flow, which is flow in between the two plates, two parallel plates, as I showed in the previous slide, okay, which is also look like this. Okay, this one is more details diagram. So since this upper plate is moving, okay, and this one is stationary, so there will be a force in this direction. Okay, so the change of u will happen, okay, as it as the delta y, as the as the distance change. Okay, so if you look at this diagram, the u or the velocity will be near to 0 when it's approached to the stationary plate. Okay, so from the equation that we derived before to determine the shear rate, actually we can rewrite the equation in order to determine the dynamic viscosity, okay, in which that the shear rate here is related to the force per area, and the velocity gradient is actually the change in velocity over the change in distance. Okay, so usually the coefficient of dynamic viscosity is derived, it is referred in the unit of kg over ms, or Newton s over meter square, or even it can be written in Pascal times second, and which is also equals to 1 point or 0.1 Pascal second. Okay, meanwhile, for the kinetic viscosity, it is much easier, in which that it is just a ratio of dynamic viscosity over density. Okay, so we already know how to determine the dynamic viscosity just now. Okay, in which that you can get it from the equation of shear rate, which is equals to dynamic viscosity times with the delta V over delta Y. So this is the dynamic viscosity. So we use this correlation to determine the kinematic viscosity by just dividing with the density. Okay, and here is the sum of the unit system commonly used for kinematic viscosity. Okay, and this one is the for SI unit, meter square per second, and this one is for US, which is used feet square over second, and other obsolete unit, which is in using the CGS system. Okay, let's do example 1. Okay, so from the question, it asks you to compute or to determine the shear stress, okay, required to pull a plate floating on a 2 cm thick layer of SAE oil. So the 2 cm here is actually delta Y, okay, at velocity of 3 meter per second, which is actually the delta V, okay. And it is known that viscosity of the oil is given here, which is equals to 0.29. So first, what you need to do is you need to get what is the input from the question and what is the output expected, okay. So from the question, outputs means that what is the question asked you to determine. So of course, the question asks you to compute or to calculate the shear stress. So you want to calculate the shear stress. Okay, what is the input or info provided from the question? Okay, the question gives you the information of delta Y, which is 2 cm, and velocity, the change in velocity, which is at 3 meter per second, and viscosity with the value of 0.29. So how can you determine the shear stress? So we know that from the formula of shear stress, which is shear stress equals to, sorry, the line keep appear. The shear stress, which is equals to the change in velocity gradient, shear stress, which is equals to, shear stress, which is equals to the change in velocity gradient, which is delta V over delta Y, okay, times with viscosity, the dynamic viscosity. So now we already have the formula. We know that we need to use this formula. Okay, so now compare this formula with the information provided from the question. Okay, let's check it one by one. Okay, the delta Y. Okay, does the info has the delta Y? Yes, which is 2 cm. Delta V. Does the info has delta V? Yes, it is 3 meter per second. What about viscosity? Dynamic viscosity is provided? Yes, it is provided, which is 0.29 in this case. Okay, this is the
dynamic viscosity provided in this question. So since the info is completed in order to solve this equation, so you can just substitute the value and calculate the shear stress. Okay, let's have a look at this solution. Okay, I arranged it already. Viscosity times with the ratio between delta U divided by delta Y. Okay, which is equals to 43. And it also can be rewrite in this unit, Newton per meter squared. That's it.
That's all. See you in the next part.